Okay, so we saw how to use new, and there are some basic pointer manipulation examples. We have two pointers. Once again, I like this example, but the problem with this is that students see this, and a lot of people think that you have to use new int, and really there's no good reason for ever using new int, because all you're doing is allocating or using setting up memory for an array of size 1. And when do you ever have to use an array of size 1? It's almost never. So this is a simple example from the book. It illustrates a lot of things, but I think a lot of students get confused by why we're doing this. Okay, so I hope that's clear. So here what you're saying is you're allocating a pointer to a single int, and then we say that, well, we're going to assign the value 42 to that heap, to that memory location that's on the heap. Then we say that P2 is going to point to the same thing as P1, and they have some nice before and after pictures. So for example, initially you have int star P1 and int star P2. They're both pointers. They're not initialized. And then after a certain amount of time, you say P1 is equal to new int. That is, you allocate memory on the heap. That's not it's not initialized. It could have 0. It could have something else, some random value. P2 is not initialized, and then you say star P1. That is the thing that P1 points to, and it's on the heap. In the past, we haven't. Whenever you use pointers, that was just a couple of lectures ago, or a couple of videos ago, we just assigned, we had P1 point to the same thing as a variable. Now this is no longer a variable. This really doesn't have a name. It's just memory allocated from the heap, and it's basically how a lot of things work in Java. You can say, I don't know if you can say this in Java. Actually, we never have to use a single int. It's not very useful, but you can say new int square bracket 1. That is, and it will have the same effect in Java. You're setting up memory for a one location array, and you'll have a pointer referring to it, although in Java we don't call it a pointer. Here we do. Okay, so when you say when you do something like, and I don't know if you can read this, this is P2 equals P1. All you're doing is you're having P2 point to the same memory as P1. That is, the address contained in P2 is the same address that was in P1. So in effect, they're pointing to the same memory location. And then if you change P2, if you have a statement like this, say star P2 is equal to 53, both of them now point to the same thing, and they both will see the same thing, 53. So if you were to print out P1, or sorry, if you were to print out star P1, after you do this, you will see the 53. Okay, you can now allocate a completely new memory location by saying P1 is equal to new int. You're allocating a memory of an array of size 1, and it's not initialized, and then you can initialize it to 88. And when you do that, P2 won't be changed. Right? Well, I mean, the thing that P2 points to will still be 53. It won't be 88. Star P1, that is the contents of memory pointed to by P1, will be new because you just set it. Oops. But P2, the thing that it points to, will still be 53. So there's a nice example here. Set up the pointers, initialize one of them, with the memory location of one of them, have them point to the same thing. Now change the thing that P2 points to, which in effect changes the thing that P1 points to. And then allocate a new memory location in the heap for P1 and assign it a value. Now this one should print out 88. The second one should print out the old value, which is 53. So I can't repeat this enough. That is, you probably never will have a reason to allocate a single int. I highly doubt it. So I don't want to see that in your code. If you do find yourself allocating a single int, you might want to think about what it is you're really trying to do, because chances are you won't ever need to do that. But take a look at that example anyway. It's just showing you how pointers work. It's not meant to be anything that you would ever need to use in a program. Okay, so we also saw this in the last video, how to allocate objects on the heap. So new, what it does is create a new dynamic variable on the heap, returns a pointer to that new variable. If the type of thing that you're allocating is a class, then the constructor is called. A constructor is called. You have your choice of calling constructors, and this part is basically same as in Java. So for example here, we did this kind of thing in the last video. We said class name star mcptr, so this says that this is a pointer to an object, an instance of my class. And initially, it's not, at the very beginning, when you just declare this, it's not initialized. It contains some random value, unlike Java, where the value of this mcptr will be null, lowercase null. That's not true, not necessarily true in C++. So this can be, this is uninitialized. And then you can initialize it by saying mcptr is equal to new, the class name, and then in parentheses you have any number of arguments corresponding to one particular constructor. You can use the default constructor as we did in the last video. Okay, so you can also do this with ints. As we saw before, there's never going to be any need to do this. This doesn't make any sense, but this is just showing you that this kind of thing will work. That said, when are you going to need a pointer to a single int that's initialized to 17? Never. Okay. So I hope those things in the book, they're just trying to help you. They're just trying to show you examples of how things work. Some of these things are never meant to be used. Like this thing, there's just no reason to ever have to allocate a single int on the heap. Maybe there are some very rare reasons. Very rarely you might run into some reason, but yeah, I can't think of any right now. Okay, pointers are full-fledged types. That is, they are complete types. So int star p, that's a type. And they can be used just like other types. They can be function parameters, as we saw. We can pass an array as a parameter, and that array could have been allocated dynamically using new. Excuse me, and can also be returned from functions. So this function find other pointer can take as an argument a pointer and return a pointer. Okay, so this function declaration has pointer to an int parameter, it's p, returns a pointer to an int variable. Okay, so memory management, almost always we are only going to be talking about the heap. Stack, the memory management for the stack is done automatically by C++. When we talk about memory management, we're looking for, we're trying to figure out how to manage memory that we allocate using new. And if you use C, you can also use other functions to allocate memory on the heap. So the heap is called, it's also referred to as the free store. That is, it's a chunk of memory that's free, and you allocate memory from it, and then you deallocate. And when you deallocate memory, you put it back into the free store, and the keyword for that in C is free. In C++, it's delete. Okay, so the heap is reserved for dynamically allocated variables. Every new dynamic variable that you allocate using new will consume some memory in free store. And if you have too many of those, you could end up using all of free store memory. So earlier on I said, you might, if you call a certain function that allocates 40 bytes at a time, if you call it 100 million times, that's more than that might be more than your complete system can have access to. Well, usually the heap is much smaller than 4 gigabytes. Actually, I don't remember exactly how much it is. On a 32-bit system, it might be on the order of 100 megabytes or 200 megabytes. I'm not really sure. So it's certainly not bigger than 2 gigabytes. Definitely not. On a 64-bit system, you have a lot more room. You might be able to set up memory for many gigabytes of space, but at the same time, you still don't want to have these areas of memory that you allocate and never use, because eventually it's possible you might run out of memory. So that's the thing to watch out for with using new. If you use new and you allocate so much memory, it's possible that some future time these new operations will fail if the free store is completely used up, that is full. Usually people think of it as being empty, but the book says full. Okay, so therefore, in older compilers, you would often check if you allocate memory and you check if it worked. If it didn't work, what you would get from new is the value null. So this p-value, if the memory allocation is successful, it'll be something other than null. But if this didn't work, let's say you used new so many times that just trying to allocate 4 bytes fails, that's possible if you used up all the memory, then p will have the value null, and so you would do something like this. You would say cout insufficient memory and exit the program. And people don't do this every single time. It's a good idea to do this, to actually check whatever new gives you, but most of the time I think you're okay. So that was the case in older compilers. In newer compilers, if the new operation fails, right now it'll be set up to, I believe, to just completely stop. The program will just stop, and sometimes you don't even see error messages in Eclipse. But if you run it on the command line, you will see segmentation fault or something like that, saying that there was no more memory. It is possible in Eclipse, if you run this, you will see no error message. So the book advises that it's still good practice to use a null check, that is, use it the old style. That is, after every new, check if it's equal to null or not, and then print out a message. Okay, well, how big is the heap? It varies with implementation. It's very large. In this course, there's no way we will have programs that will actually need all of the memory, even on a 32-bit system, which only has a max of 3 gigabytes for your program. That's besides the kernel space. Total of 4 gigabytes, 1 gigabyte for the kernel, 3 gigabytes for your memory, but not all of that is going to be heap. That's going to be, part of it's going to be the memory taken up by the program, and then by the stack. And heap, I'm not really sure exactly how much it is on a 32-bit system, but it's definitely, I'm going to guess less than 2 gigabytes. Okay. On a 64-bit system, yeah, it's going to be much larger, but I'm not really sure. It's going to be more than 2 gigabytes, definitely. But it's still good practice to check every check and make sure it worked. It's just a good way to write solid software. Memory is finite, regardless of how much there is. So if you have a 64-bit system, don't assume that you have an infinite amount of memory.